Every second, billions of digital transactions move across the global network. We tap our screens, and data crosses oceans to confirm a flight, send a text, or buy a coffee. When you hit a Pay Now button, you initiate a single high-stakes user action. You tap it exactly one time, expecting one clean result. But the trust breaks when you check your bank statement. You see the exact same charge listed twice, as if you had authorized the transaction twice. This usually isn't the result of a bad line of code. It is a product of physical reality. If the network drops for even a fraction of a millisecond, the connection between your device and the server shatters. In the silent retry, the phone sends a payment packet, but a barrier blocks the receipt. Assuming failure, it fires a duplicate packet. At the server, this duplicate arrives clearly. A naive server blindly processes it as a brand new order, printing a second receipt. This auto-retry is a helpful feature for stability, but it creates a catastrophic structural flaw if the receiving system trusts every signal it receives. To solve this, engineers shift focus away from the user's phone and into the backend server environments where these requests are processed. The dilemma for the server is one of intent. It has to distinguish between a user deliberately making a second purchase and a phone firing a panicked network retry. If you look closely at the raw data, the purchased item, the price, and the user profile, the two payloads are completely indistinguishable. Consider the invisible mechanism at work, the request ID. While the outer packets look identical, peeling back the shell reveals a unique alphanumeric sequence stamped inside. When the network drops and retries, it doesn't create a new identity, it sends the exact same stamp. This allows the server to perform a verification step. It checks this ID against a database of recently processed requests before any money is moved. Preventing the duplicate problem requires moving the burden of trust away from the unreliable network and onto this cryptographic receipt. Let's return to the moment of the failed transaction to see how these new rules change the outcome. The connection drops, and the phone fires the duplicate payload as it did before. But now the server is protected by a defensive posture called idempotency. In engineering terms, idempotency is a rule where repeating an operation multiple times produces the exact same result as doing it once. In this simulation, as data blocks move down the track, a scanner identifies the duplicate request ID and immediately diverts it, preventing the secondary payment from ever being processed. The server doesn't just block the request, it resends the original success receipt to the phone. This gracefully resolves the network confusion. The phone stops retrying, and the user's actual state remains unchanged. This logic dictates the structure of every major digital platform operating at scale. Idempotency is the safeguard for task creation, order processing, and message delivery. Without it, the modern web would be a storm of duplicates. Digital networks are inherently messy. Dropped signals and retries are not anomalies. They are constant, guaranteed occurrences. To build resilient systems, developers must abandon the assumption that a request will succeed on the first try. The mandate is to design for the messy multiple, assuming that duplication will constantly bombard the system. A resilient system survives by mathematically guaranteeing that repeated chaos cannot change the truth. But that truth becomes much harder to protect when the data isn't sitting on one server, but is split across 10,000 machines simultaneously.